Okay, let's get back into fun things. Any questions from the first half? So I forgot to mention in the lecture notes, I'm actually skipping over this section called regular grammars. I will come back to that at some point. Because it segues better into the next material after this. But we will come back to regular grammars at some point. Okay, so we were talking about this this language 0 to the n, 1 to the n. Equal number of zeros then followed by equal number of ones. And we had an intuition of why there's no DFA for this, because the DFA can't remember the string. But this is not a proof in general. So the way that we're going to go about this is we're going to talk about the strings. If we have, for example, some string that's recognized by this, that's accepted by this DFA, then from that string, we can describe other strings that this DFA also says accept to. And then, so therefore, that this DFA's language has a property, not the same property as Rice's theorem, but it has a property on the strings in its language. And so, since every DFA will show has those types of properties on those strings, if we can show a language does not possibly have a property on those strings, could there be a DFA for it? No, because it's just the contrapositive of that. If it has, if you have a regular language, then it has some properties. If we show a language does not have those properties, it could not possibly be regular. And so that's how we're going to go about it. So let's see. Anyone remember the pigeonhole principle? What does the pigeonhole principle say?
There are like n things, and we have n things to configure in them. Then if n is less than n, then one of the n would be repeated.
Right, exactly. So if we have more pigeons than we have pigeonholes, then there must be some pigeonhole that has two pigeons, if all of them were put into some pigeonhole. So I want you to think about that when we think of this. So let's say that this DFA has n states, for now. What if I feed into this DFA a string of length n, exactly n? What has to happen? How many states will we see with an n-length string? N plus 1. Pigeonhole, pigeon. What has to happen? Some state repeated, right? So if we feed in a long string, say at least the number of states, some state will repeat along that way because we see at least n plus 1 states and there are only n of them. We may see one state many times, and we may see some states 0 times, but there's some state that we saw at least twice along the way. So let's say that we have a string w1 through wn. It actually doesn't matter here. Then some state, and also we say that the DFA accepts DFA accepts this string w. So when we feed this string w to this DFA, what state do we end it? One of the final states, right? Well, I don't know what happened before that, but I know first off that we started at the start state and we read some number of characters, maybe 0, but some number of characters. And let's say we go to the final state at the end. So eventually we will read some characters that will lead us to a final state. Say that one. But along the way in the middle, we had a state repeat because we made the string equal to the number of states in the DFA. So let's say it's this state in the middle. So this picture may make it seem like this state is completely different from the start state and from the final state. They could all be the exact same state. It could be that this state in the middle is the same as the start state, completely different from the final state. Any combination is possible, but I'm just making this look like a general thing. Well, since we said this state repeated, there must be some number of transitions that happened when we first entered that state. We read some more of the string, and we eventually came back to that state. It may be in one transition, it may be in a million transitions, but we eventually came back to that state. So let's say we did this. It may be, what do we know about the lengths of these paths along the way? What do we know about this first path along the way? What do we know about the length of it? Well, it's definitely at most n, but could it be 0 characters long? Yeah, certainly. So because I said it didn't have to be a different state than the start state. So maybe it could be 0 characters long. Could it be more than 0? Yeah, certainly. It could read some characters, then go to a loop state, go to a state, then repeat, then eventually go to the final state. So this could be at least 0 characters. And the same reasoning applies to the third part over here. Chars. What do we know about that middle set of transitions? Could that be 0 characters? No. Why not? Well, it must have one transition along the way, but could that transition be an empty set transition, empty string transition? No, why not? Because it's a DFA. So the at least one transition we see must have at least one character on it. Okay? So this piece has at least 1 characters. Okay? So let's blow this up a little bit. So let's see. Let's call the strings that we see along the way certain names. So let's call this first string, let's call it X. Let's call the middle piece Y. And let's call the ending part Z. What is W equal to? It must be X, then Y, then Z, correct? So it must be X, Y, Z, right? Because that's just how we decompose the set of transitions we saw along the way. Question, is X, Y, Z accepted by the DFA? Yeah, because we just follow the diagram, X, Y, and then Z takes us to a final state. What about XZ, the string XZ? That's a different string, but is XZ also accepted by this DFA? Yeah, because we just now ignore, well, not really ignore, but we're not going to take this looping part in the middle anymore. So we're going to follow X, then follow Z. So XZ is also in the language of the DFA. So let's say L is the language of the DFA. What about X, Y, Y, Z? So I have Y twice. So again, a different string. Yeah, that's also in the language because I follow X, follow this looping thing twice, and then Z takes us over. So that's also in the language. By the way, once we read that Y, does the DFA have any recollection of seeing that first Y? No, so that's how the notion of not remembering is going to be formalized here. So that we can repeat this Y thing, this looping part, as many times as we like. How about any number of Y's where I is at least 0? So yeah, because it's just exactly the same thing, but I have this looping part, I repeat it I times. But so that's also in the language too. Oh, wait a second. What do we know about the length of Y from our earlier discussion? It's at least 1 in character. So we know that this condition must hold for an arbitrary DFA. we must have that y is at least 1. The length of y is at least 1. So another way to say that is y is not the empty string. Did I pick originally a string of length exactly equal to n? Yeah. Could this work, this idea of repeating, does it work for any number of characters at least n? Yeah, because the pigeonhole principle still applies. If I have more states that I see than there are states, then therefore we'll still have a repeating thing. But now let's consider when we have exactly n characters. So we have the same pictures we had before, but let's consider when we have exactly n characters. What do we know about the length of x, y? Can that be more than the number of states in the DFA? No. So this indicates the first repetition of the y part. So the repetition of that state. So what this says is that when does the first repetition have to occur? Well, it can occur very late, but how late could it happen? Well, could it happen at the n plus 1 character? No, because if we look at the first n characters, then by our argument from before, we must repeat a state within the first n characters. Because if we have n characters, that means we have seen n plus 1 states, which means we must have seen at least one repetition. So this says that the first repetition must occur before the nth character of the string. Does that make sense? Okay, so in fact we just proved one of the most important theorems in about regular languages. And so the name of this strikes the fear in the hearts of many CS students across the entire world, but we just proved the pumping lemma for regular languages. Dun, dun, dun. Okay. So it says the pumping lemma for what kinds of languages? Regular languages. So regular languages are described by DFAs. So I'm not going to say the word DFA anywhere in the description of the lemma. Oh, by the way, what does lemma mean? So lemma usually just means a helper theorem. So it's like a mini theorem that's like an important result, but it helps prove other theorems. So the use of this is to help prove that some languages are not regular. But it's not going to say non-regular anywhere in here. It's only going to talk about the types of strings that regular languages have. So we're going to let L be a regular language. So it has a DFA, but we're not going to think of we're not going to write down the DFA. But in the back of our mind, we're going to think back to our picture up here about this end state DFA. So what had to happen for us to derive the conclusions that we did? What if W was shorter than the number of states? Could we conclude this? No, I might not, in fact, repeat any states at all, right? But if I did have W equal at least to the number of states in the DFA, then I could because of the pigeonhole principle. So we can only talk about strings at least the number of states in the DFA in length of that string. So then there exists what is called a pumping constant. We're going to call it P. So the constant P here is the n that we saw before, the number of states in the DFA. So I changed notation because P is a standard letter for this type of thing, for the pumping lemma. So remember, we're only talking about strings in the language, right? If I was talking about a string that ended up in a non-final state, could I conclude the same thing about strings in the language? No. In fact, I'd be talking about strings not in the language, but I'm only talking about strings in the language. So we have to talk about all the strings in L at least this constant long. So for, I should not say that. Then there exists a pumping constant P for which, for all strings in L with at least P characters in them. So for all sufficiently long strings, then we can break it up into this XYZ thing where we can repeat the middle part and we can guarantee other things about the X and the Y parts. So could there be many ways to decompose the input into this XYZ part? In other words, could there be many places where we repeat a state? Yeah. In fact, there may be one over here, right? So there may be many ways to decompose a string, but there is one for sure because we forced the string to be long enough so that we have this repetition. So for any string at all with this length constraint, then there exists a decomposition W into X, Y, and Z. So it's exactly like our picture before where we have this X part, the Y part that repeats, and the Z part after, such that, almost there, we have three conditions. And it's actually precisely the same three conditions that we had before. That the length of xy is at most p, so we're guaranteeing when the first repetition happens. The length of y is at least 1, same thing as before. We need to have at least one transition in the DFA to have it be a repetition. And x, y, so I copies of y with the x and z parts at the end is in this language for all I at least 0. Okay? So it's exactly our picture from before, but now we're just generalizing it to any arbitrary regular language. Yeah?
Well, when you prove that y, the length of y is greater than or equal to 1 and xy is less than or equal to 1.
So remember, the y is at least 1 because in the DFA, when we had the repetition, we had to have at least one transition around. So therefore, since the transition had to have some character on it because it's a DFA, then the length of this looping part must have length at least 1. And the xy having length at most p characters, the reason for that is we're trying to guarantee when the first repetition occurs. Okay? So if we have p states in this DFA, then the first repetition must occur within the first p characters, right? Because of the pigeonhole principle. But the first repetition is when the y part ends. So remember, the y part's the repetition part. So if we include the x part and the y part, that's from the beginning to end, that's when the repetition occurs. So the last character of y better be at most the last character of y better be at most the pth character in the string. In fact, this is just a thought exercise. This first condition is actually not needed, but it's a very, very helpful tool to help us prove that languages are not regular. The second and third condition are absolutely needed, but the first one actually isn't needed. Any other questions about this? Yeah.
How do you prove that it's not regular?
Great question. So how can I prove that a language is not regular? Well, let's see. Well, it says that for all W and L with length at least P, right? So let's pick one. Let's pick one W and L with length at least P. If we can show for that string, there is no way to decompose that string into 3 pieces at all. There's no way to break it up such that these 3 conditions hold. Is the for all statement true? I just found one string that is an L with length at least P, so it better be true for this string. And if we can show there's no way to break it up into 3 pieces with those 3 conditions holding, then didn't we just show that this for all statement is not true anymore? So in fact, L's regular language, it said that for every string this works. So if we suppose it's regular, this language that we're looking at, we suppose it's regular, then if we can find a string that's like a counter example to this for all statement, then doesn't that show that it's not regular? Because it's a regular language, that implies every string works, but we just found a counter example. Wouldn't that be enough? I need more people agreeing. Would that be enough? Okay. Yeah, so we're going to do an example, yeah. But any questions about like how we came to this statement of the lemma or the ideas behind it? Cool. So let's actually prove that that language that we talked about is actually not regular. So let's talk about this language again. And we'll show it's not regular. So if you're faced with a question like this, you have to show that some language is not regular. What's a common way to try to prove that that's true? What's a common technique to prove something to be true? Well, like in the ATM proof, how did we go to show that it was undecidable? Yeah, we did a contradiction. We supposed it was decidable, then we derived an inherent contradiction. Exactly the same thing here. We're going to suppose that it actually is regular, and then we'll derive a contradiction. And so therefore it can't be regular. Okay. So let's suppose L is regular. Okay? Maybe we're completely wrong. There is some DFA for this. Well, what did this pumping lemma statement now tell us? We suppose it's regular. Now what are we guaranteed? Yeah, this constant P thing, right? Pumping lemma says that if we have a regular language, then there's this constant P for this language, whatever it is. Okay, so then there exists a constant P for L. Can I assume that P is equal to 2 or 10 or a Googleplex? Do I know what this constant P is? Does the lemma tell me what the constant P actually is, like the number itself? No, there exists a constant. I don't know what it is. So this is actually a red herring for when we pick a string, right? Because we need to pick a string that's in the language and has at least P characters. So I'm going to pick a really bad string. So I'm actually going to pick 2 bad strings. But so I'm going to actually say that it's bad. Let's choose as our possible counter example string W to be 0, 1. Well, it's in the language, right? It's definitely some number of zeros followed by the same number of ones. But is it long enough? Probably not. I don't know, because I don't know what the constant p is. I can't guarantee that it's long enough. Okay, so that's a bad string. Let's not pick that one. So this one's another bad one. So let's choose p zeros. It's definitely long enough. So I've learned my lesson. The string is long enough now. What's there? Technically no, but it's actually not needed here. We'll actually never assume anything about the constant itself. We just know that there exists one because we assume that it's regular. Well, can I pick this string? No, why not? It's not in the language, so let's not pick this one. Now, so I've learned my lesson twice now. Now you tell me a good string, or a string that you think might work. P zeros followed by P1s. I think that's a good string too. So so W is definitely in the language, and the length of W is 2P, but that's at least P, so we're okay there. Okay? So what do we need to show? It says here, there exists a decomposition into 3 pieces, but I want to show that there's no way at all to decompose this string into 3 pieces. Because if there is some way that works, then maybe this string, however we try to pump this string, so I should say, this part of putting an extra copy of y in is called pumping the string. But if we leave out some decomposition, then maybe that's the one that works. That there exists decomposition, so maybe that's the one that works. What I want to show is there's none that work at all for this string. Okay? Well, how many decompositions of a string into 3 pieces are there? A gazillion, right? So this is where the conditions will help us. What does the first condition tell us? That the x and y pieces together are at most p characters. Oh, what are the first p characters of this string? Zeros, right? They're all zeros. Well, do I know how many zeros the x and the y part have? No idea, right? I know that y has at least 1 0, but could have many more. X could have 0 of the zeros. Could be any number of them. So what we're going to do is let's handle all of those possible cases in one step. Another question. Could y contain any of the ones? No, why not? It's after the p character. So that's where it'll actually help us here. So let's see. I don't know what the x, the y, and the z parts are. I know that x and y themselves contain some number of zeros. I don't know how many, but it contains some number of zeros. So let's say that x has alpha zeros, some number of zeros. I don't know how many. Could be 0, could be more. So actually we should say alpha is at least 0. We won't actually use that, but it's good to be in that habit. Again, for y, it's some number of zeros, I don't know how many. It may be different than x, it may be the same, I don't know. But let's say it has beta zeros. What do we know about beta? Beta is at least 1 because of the second condition. Well, is z the rest of the string? Oh, let's see. How many zeros do I have left over after I've taken the x and the y parts away? Well, I started with p zeros, and I took away alpha, then I took beta more of them. So in fact, I have p minus alpha minus beta zeros left over. This number actually might be 0. X and y may take all p of the zeros. It may take fewer, I don't know. I'm handling every possible way in one step. But z must have all of the 1s left because the x and the y parts have never touched the 1s at all. So I have all the p's, all the ones left. Good so far. Any questions? So let's briefly go back to the statement here. Let's see. So if we look at, we are looking at every decomposition right here, every way to decompose according to these rules. If I show that there exists a value of I for which we are not in the language, does that contradict the for all statement in the third condition? So it says that for all I at least 0, x with I copies of y, z, is always in the language. If I pick a value of I for which it's not in the language, does that just contradict what we want to do? Exactly. So now we got to pick a value of I for which x, y to the I, z is not in L. What value of I should I not pick? 1. Why should I not pick 1? Yeah, it's just the original string back. And what do we know about the original string? It's in the language. So, in fact, I'll tell you right now, every other value of I will work here. But can you give me another value of I? 2. 2 is a perfectly good one. So let's pick I equals 2. Okay. Well, what the lemma says to look at is, let's look at x, y to, not I, let's put 2 there. So this is usually called squared, even though it's not really squared. It's just a term in the literature. So this is just 2 copies of y and x and z at the beginning and end. Well, what is this string? Well, let's just look at our arbitrary decomposition and just copy down the pieces. So the x part, it says, I have alpha zeros here. Now we have 2 copies of y. So how many more zeros am I going to put there? 2 beta zeros. So I'm going to put 2 beta there. And it says z, so I'm just going to copy down z directly. So p minus alpha minus beta, and all of the 1s. Okay? So it seems like we have a whole bunch of runs of zeros here. Could we just collapse all the zeros into, yeah, go ahead.
That should be p minus alpha minus 2, right?
No, it should be beta, because I'm copying z down here. So I have 2 copies of y, but I have 1 copy of z.
Aren't there beta copies of the 0 in y?
Yeah, but I have, right here I have 2 copies of y. So I'm trying to increase the number of occurrences of y that I have, and because of that, I'm increasing the number of zeros in this. So it's a completely different string here. But I'm looking at a different string to hopefully show it cannot possibly be in the language. That's all we're trying to do. Does that answer your question?
I don't think so. Where'd the alpha go?
Well,
In the C.
it's still up here. It's right there.
Oh, I thought that was in 2.
Oh, sorry. See, if I have atrocious handwriting, and I do, you won't hurt my feelings. Just tell me, and I can fix that. Yeah, should be alpha. Sometimes I use A and B here, but sometimes it confuses with the characters. So, okay. Any other questions about that? Okay. Well, I have a whole bunch of zeros here. Could I just squash them all together? Well, let's see. If I have alpha at the beginning, doesn't that cancel with the minus alpha over here? So I have alpha at the beginning, and I took away alpha there. I have 2 beta at the beginning, but I only take away 1 beta at the end of the set of zeros. So how many zeros do I have left? Right. So I have p plus beta, and I never touch the 1s, which is key here. I never touch the 1s. Can this resulting string be in the language? No. Why not? Well, the only way it could, so this will seem very tedious, but the only way it could be, so it's in L if, and only if, P plus beta equals P, which is the same thing as saying that beta is equal to 0. But this is a contradiction, as you rightly pointed out, because beta is at least 1 from above. So in fact, we just showed that the pumping lemma for regular languages would tell us that this string has to be in the language if it was a regular language. So if L was a regular language, then this x, y squared z, that also has to be in the language. But there's no way it could be because we defined the language this way. So what can we conclude about L? It can't be regular because if it were, then we wouldn't get a contradiction at the end, but we do. So because of that, L is not regular. I get goosebumps every time I prove that. It's so cool. I love this stuff. But any question about why we were able to get a contradiction at the end? Yeah.
Can you explain again why you used 2 instead of, or why you didn't use 1?
Right. So I'll ask you guys. Why didn't I use 1 for I equal 1? Yeah. Right. Exactly. So x, y, 1, z is just the same thing as x, y, z. It's just one copy of y, right? But isn't that just the original string that we started with? Because I decomposed w into x, y, z. But we started with w being in the language. We had to pick some string in the language, right? But we're trying to get a string knotted. So never pick 1 because it'll never help you. Very often, you can pick any other value. Sometimes some values of I work, some don't. Sometimes only one value of I works. I can do that example if you want. Yeah, but yeah, go ahead.
The third condition in pumping lemma says I is greater than or equals to 0.
Mm-hmm.
Why can't we take I is 0?
Oh, so I'll ask you, why can I take I equals 0? So what would that be? Just xz. Yeah, so I can actually take away a copy of the copy of y. And so I would have xz at the end. It's just a different string. Any string taken 0 times is just the empty string. Other questions? Yeah.
You could also go like 0p and then split up the y.
No, I can't because xy is a prefix of the string. Remember, I decomposed it into x, y, z, and xy is the front of the string, not the end. If I change the language to be 1 to the end, 0 to the end, then you would be working in the ones, but you're still working in the front of the string. So I mentioned that first condition is not necessary, but the proof of not using that first condition is a lot longer than just using it, so that's why we use that first condition. Other questions? I can actually tell you why we don't need it. So the way you go about it is, if you look at any p-length substring, not necessarily at the front, but any p-length substring, then in fact you'll still get this repetitious behavior in the DFA. So what we'll need to do if we want to ignore the first condition is look at any p-length substring anywhere in the string. And the only problem with that is if we look at the front, we know how to handle that now. If we look at the ends, we can handle it very analogously. But the only issue is, what if the XY part straddles the middle of the string? The repetitious part straddles the middle of the string. Well, it's a lot harder to deal with that. So that's why we only deal at the beginning of the string and force the first P characters to be the same, so that the cases we need to deal with is exactly 1. So that X is some number of zeros, Y is some number of zeros. We don't need, like, okay, if X starts with a 1, then Y must start with a 0. Or if x has this, then y must be this. We know what the x and y parts look like. Okay, any other questions? Cool, let's do another example. Oh, that'd be too complicated. Okay, so let's call it L2. So it's almost the same language, not quite the same. But W has the same number of zeros and ones. Why is this not the same language as before? Right. In the first example, we did have the same number of zeros and ones, but the zeros had to be before the ones. Here, they can be in any order, right? Zeros can be followed by ones, one can be followed by zeros, any order you like. So I want to claim that this is not regular either. And in fact, there's a very, very short proof for this. Actually, two, but one very short. Wait, what if we look at the exact same proof from before? If we look at this, if we pick that string, is this string in L2 same number of zeros and ones? Yeah, it's the same number of zeros and ones. It just happens to be zeros followed by ones. Well, do we get a different number of zeros and ones at the end? Yeah, we get a different number of zeros and ones at the end. So in fact, we leave L2 as well. So in fact, this is not regular using same proof. Which is pretty cool. But I want to show you a different way. Suppose L2 were regular. So we're not going to do a pumping lemma proof, but we're going to use the fact that the last language we looked at, 0 to the n, 1 to the n, is actually not regular. Well, how do I get from any order number of any order zeros and ones to the language that has zeros followed by ones, the same number of both? Well, let's see. The language from before has the same number of zeros and ones and zeros followed by ones, right? That's what the relation is between these. So how do we write the same number of zeros and ones and zeros followed by ones? Here's how we do it. L2 intersect 0 star 1 star. Well, we don't know the answer to L2 whether it's regular or not. Is 0 star 1 star regular? Yeah, how do you know? It's a regular expression. See why we do regular expressions? So it helps us in proofs like these. So we know that that guy's regular. Oh, what is the resulting language? It's the same number of zeros and ones and zeros followed by ones. Oh, it's that language we just talked about, the 0 to the n, 1 to the n language. And we just proved that this is not regular, right? That's what we just proved using the pumping lemma. Suppose L2 were regular. What is the left-hand side? Ah, it must be regular. Why? If L2 were regular, a regular language intersect another regular language, what does that have to be? Regular, because closure under intersection. But the right-hand side is not regular. So could L2 be regular? No, because if it were, then the right-hand side would be regular as well. So in fact, from this, we can conclude L2 is not regular. So using closure properties actually really helps in some of these proofs, and that you don't have to deal with these pumping lengths and whatnot. You can actually just relate it to an already non-regular language using closure properties like this, which is pretty cool. Yeah?
So if we have a test or something, we didn't necessarily have that one, we just pull it up and say, like, we proved that in class.
Right, yeah. I mean, don't do what some of you did, which is like if you see where is it? If you see this language on the test and you say we proved it's not regular in class, what do you think I'm going to give? Yeah, so yeah, don't do that. But if you're referencing like 0 to the n, 1 to the n, or this one is not the same language, yeah. So I'm almost guaranteed to not put the exact same languages that we do here, but maybe a slight variant. But any other questions? Yeah.
So maybe I'm missing something, but the left-hand side, this, to me, doesn't necessarily have to equal the right-hand side.
Why not?
Well, for instance, L2 could be 0, 1.
No, L2 has a whole bunch of strings, yeah.
Okay, yeah, I get it.
Yeah, okay. Cool. Any other questions? Yeah.
Can we have a short example of a regular language that can be proved that it is the regular?
You can't prove that a language is regular using the pumping lemma. Why? Because the pumping lemma at the first sentence says you have to start with a regular language. So you can't prove that the language is regular because you have to start with it being regular. So that's a good question. Actually, a good test question too. But yeah, you can't prove that a language is regular using this. You can prove it's not regular because it's just the contrapositive of that.
And for any other language given, alpha, beta is the approach that we should take.
Yeah, in the general case. But you need to handle all possible cases because it may be that sometimes you start with a 1, sometimes you start with a 0. But it depends on the string that you pick. Any other questions? So let's do one more that I think is really cool. So do you want me to semi-warp your mind or really warp your mind?
Semi.
So I can either talk about perfect squares or primes. Pick perfect squares. That's actually the better one for you guys. All right, so let's talk about SQ, this language, which is, so I'll just write it down first. So the language is just a perfect square number of zeros. So 0 zeros, 1 0, 4 zeros, 9 zeros, 16 zeros, need me to go on? 25 zeros, 36 zeros. So this is the language of perfect squares, and I claim it's not regular. So this is actually where a little bit of high school math comes into, actually grade school math comes into play. Anyone remember how to FOIL? Okay, so that's all you'll need to do this. And 355 knowledge, I guess. But all right, so how should we start a proof like this? Suppose it is regular. So suppose SQ is regular. And because of that, we now know that what exists? Some pumping constant P, yes. So then exists pumping constant P for this language SQ. States quarterly? I don't know. Okay, so there exists this pumping constant P for this language SQ. What do we do now? We have to pick what? Pick a string that has what two properties? It's in the language and a length at least P. Can you give me an example? Yeah, P squared. That's a perfectly valid one and the one that'll actually work here. Well, the great thing about working with unary languages, so languages with only one character, is that the decomposition part is really easy because there's no other characters to actually worry about. So X, it must be some number of zeros because the whole string is zeros. So let's say it has alpha again, Y has beta again, and Z has, well, now we started with P squared, and we took away alpha, then took away beta. So now we have P squared minus alpha minus beta. So, okay, so now we picked the string. We're looking at an arbitrary decomposition now. And then, so what do? We pick a value of I and then want to look at x, y to the I, z. So which one should we pick? 2. And this is actually the only one I think that'll work for this case. So let's pick, I think other ones will work, but I know 2 works. So let's pick I equals 2. So again, let's look at x, y squared, z. So how many zeros will I have now when the dust settles? Well, didn't I just add beta to the original string? Yeah, so how many will I have at the very end? P squared plus beta. Good. So I have p squared plus beta. Well, okay, well, do I know that p squared plus beta is not a perfect square? Might be equal to 1, right? If it's equal to 1, then we're toast. But if we can show that this cannot possibly equal to a perfect square, are we done? Cool. Moreover, even more importantly, if I can show it's between 2 consecutive perfect squares and not equal to either one, could it be equal to a perfect square? No. So that's actually what we're going to do. What is the smallest that beta could be? 1. Okay, well, let's see. So we're going to have some inequalities here. So I know that this, whatever this is at least p squared plus 1, because that's the second condition of the lemma. Oh, that's strictly more than this perfect squared p squared, right? So can p squared plus beta be equal to p squared? No, it can't. Well, could it be equal to, say, the next perfect square? Maybe. So, well, what is the next perfect square after p squared? Ah, p plus 1 squared. Oh, what is that? So this is where the FOIL comes in. P squared plus 2p plus 1. Okay, that's fine. But I don't know how large beta could possibly be. Or do we? How large could beta possibly be? P. Why? Because xy has length at most p. Could x be the empty string? Yeah, there's nothing in the description that says x can't be the empty string. Y can't, but x certainly could be. Oh, so I know that this... You okay? Number 1 in innovation. So I know this p squared plus beta is at most p squared plus p, because beta can't have more than p characters in it. What's the relation between these two? Ah, even if p were 0, this plus 1 will get us, right? So that must mean that the maximum length that this string could ever be is strictly less than the next perfect square. Oh wait, so let's recap. We have 2 consecutive perfect squares, and it's not equal to either one of them, and it's in between. What do we know about the length of the string we just got? It can't possibly be in the language. So what we can conclude from this is that it's not in this language SQ, because it's between 2 consecutive perfect squares. Oh, so what do we know about SQ now? Can't possibly be regular, because if it were, then we would always be equal to a perfect square, no matter how we pump. But we just showed a way that it doesn't. So SQ is not regular. Would it be equal to a perfect square, you mean? Well, the trouble with that is that you have to well, you have to assume first that the language is regular. But I mean, you're looking for an example for which we do equal a perfect square. So if you pick I equal 4, then you'll have a length string p squared plus 3 beta. And so that the next perfect square is in the range of what the length of the string could be. So in fact, I equals 3 also works. So can anyone tell me why I equals 3 also works for this problem? What would be the length of the string at the end if we picked I equals 3 instead? Plus 2 beta. Well, let's see. If we had, so let's make that red. If we have 2 beta there, then at most that's at most 2p, but we're still strictly less than p squared plus 2p plus 1. So in fact, I equals 3 works here. So I equals 4, you can't guarantee it's not a perfect square. But for I equals 2 and 3, you can. So the most common cases are when you pick I equals 0 and I equals 2. But as long as there exists one value of I for which you get out, that's all you need. Okay, any questions about these examples? Yeah.
Like these are the ones. The format of the question on the test is very similar to this. Like you have to pick an I.
Yeah. So I would say show that this length, or maybe say I have a language and you have to show whether or not it's regular. So if it actually is not regular, then you need to show that there exists a pumping length p, which you do by supposing that it's regular. You pick a string that first is in the language and long enough, because otherwise you can't say anything. Then you need to handle every possible decomposition, which we do here. Then you need to pick one value of I for which you can show you leave the language. Okay? Yeah.
So if there was a question that says shows this is non-regular,
Mhm.
at the beginning of this lecture you explained how you could draw, a DFA
Mhm.
and then make a longer string.
Yeah.
Would that be a valid proof?
No, because you're working with a single DFA. You need to show every possible DFA doesn't work. And I don't think you have enough time to write down infinitely many DFAs.
I mean, couldn't you just say this would require infinitely many DFAs?
But that wouldn't be a valid proof. How would you handle the other DFAs? How would you know that they don't have the right language?
Because they don't have enough states.
Well, the number of states doesn't matter. As long as there exists, so this exists pumping constant p, in the back of our mind, that just means there exists a DFA on p states. And we're supposing that it does have the right language SQ. And then we're saying, well, I don't know what this DFA looks like, right? Some DFA, and we're supposing it has the right language. Then if we pick some string that it must accept this W at the beginning, right? Because it's a perfect square. So it must say yes on that. Then, because it's so long, we can break it up into those 3 pieces that it repeats. And then we just said, well, consider this the string where you go around twice, right? It must accept that one too, right? Because there must be some way to decompose it into those 3 pieces. But we looked at every possible way of decomposing the string and showed none of them possibly work. Meaning that the resulting string is not a perfect square, but the DFA always says accept on it. So that means the DFA cannot possibly have the right language. So I assumed that it was an arbitrary DFA in the back of my mind, and then showed via this that the DFA must accept this longer string, but this string should not be accepted at all because it's not in the language. Okay? Yeah. We can do an example in office hours if you like.
For choosing a string within the language,
Mm-hmm.
would it generally be a wise strategy to replace the variable like n?
With P, yeah. Yeah, that's the usual strategy. Sometimes you can't. I can do an example in office hours. But sometimes you need a p plus 1 in one place and a p in another place. So, but generally that's the right idea. I still have 22 seconds. Any other questions? Yeah. Good question. I don't know. I'll have to think about it. I know a related question very close to that is it's not regular, but I don't know about that one in particular. An open question. Okay, well, I'll talk about that next time. So it's not quite the same. Think about, instead of perfect squares where 0 to n squared, think about primes. Try to show that that's not regular. We can talk about Piazza about that. So I'll see you on Monday. Pick up your test if you haven't yet.